Thank you so much, Matt. It's a tremendous pleasure to be here. The title of the talk is Human+AI, or Artificial Intelligence, Approaches to Improve Real-World Accessibility. And today I'll be talking about a sampling of projects that incorporate sensing, machine learning, and user interfaces to improve real-world accessibility. This work is done primarily by students in my group, the Makeability Lab, which are shown in this picture during, of course, pre-pandemic times, as well as collaborators at the University of Washington, UMD, Gallaudet University, and beyond. The Makeability Lab's mission is to design, build, and study interactive tools and techniques to address pressing societal challenges. And we like to think about opportunities and research problems at the convergence of the physical and digital worlds, or what Hiroshi Ishii might describe as bits and atoms. For example, how might new sensors or machine learning approaches be used for energy auditing in buildings, or to support personalized routing for people with mobility disabilities? We work across 4 primary areas: environmental sustainability, health and wellness, accessibility, and STEM education. And of course, today I'm going to be talking about that 3rd area on accessibility. But I want to give you a broader overview of the work that we do in my lab, starting with environmental sustainability. So for example, here, we're working in an area called pervasive thermography, developing mixed initiative capture and analysis tools that allow citizen scientists to easily and accurately audit thermal leakages of buildings using their smartphones. For health and wellness, my collaborators and I have examined the use of behavioral theory to support health promotion and built systems like Social Fabric Fitness, shown above, that operationalize this theory in design. In the video, I'm showing a custom e-textile display that shows group running information like pace and distance. In our deployment studies, we found that these jerseys helped improve awareness of group performance and motivated them towards shared goals. And of course, these focus areas are interlinked and synergistically related. For example, in the Body Visit project, we created e-textile shirts that sense and visualize a child's physiology and allow them to draw connections between human activity and their health. Here's an early prototype with fabric organs, embedded LEDs, and electroluminescent wire to show the wearer's heart rate and oxygen exchange with the heart. And a later prototype that senses and visualizes real-time heart and breathing rate, which adapt to the children's activity. But today's talk is primarily focused on accessibility. In particular, how to make the physical world more accessible for people with disabilities by sensing, processing, and feeding back information about physical phenomena in new ways. I will provide a rapid tour through 3 projects with a longer emphasis on the last. And all 3 incorporate sensing, machine learning, and feedback to improve access to the physical world. In the first project, we're investigating methods to sense and feedback non-tactile information as it is touched for people who are blind or low vision. To begin, I want to show a video highlighting the various ways we use our hands to feel and sense information. In particular, for people who are blind or low vision, touch is a primary means of acquiring information about the world. Prior work in neuroscience and psychoperception has found that blindness can enhance tactile acuity. However, fingers can only feel tactile phenomena, bumps, temperature, and shape, and there is much richness in the world that is non-tactile. So in our work, we're exploring how to computationally augment a blind person's sense of touch to interpret non-tactile information about the world, such as color, texture, and printed text. Imagine, for example, gliding your finger along a printed text and hearing the words read back to you in real time, or feeling the shape of a bar graph in a book or newspaper, or touching a piece of clothing and hearing a description of the underlying fabric. In the Handsight project, we explore a wearable computer vision augmented touch system. Handsight consists of 1 or more tiny endoscopic cameras worn on the finger, typically used in non-invasive surgeries. This tiny size allows for new wearable form factors not previously possible. For example, placing cameras under acrylic fingernails, instrumenting multiple fingertips, as well as various ring designs. To guide the user's touch explorations, the camera is paired with microhaptic actuators embedded on the finger and/or wrist. And a smartwatch is used for processing and power, as well as additional sensing and feedback. This research is application-driven, drawing on research literature and formative interviews to address key activities of daily living, like reading printed text, shopping, or getting dressed. To support these activities, we have built and evaluated systems for reading support, color and texture recognition, touch-based control, and haptic and auditory feedback. For example, in initial work, we focused on real-time reading support of printed text as shown in this video.
Any dog on the toy testified that dogs are just as prone to jealousy as humans.
To help guide the user's hand, we've run experimental studies comparing different haptic signals and bracelet designs. We've also explored reading support for low vision users using head-mounted displays and finger-worn cameras. For example, here, we're watching a user magnifying text with their finger and seeing a higher contrast and large version in their heads-up display. They can then use gestures to change how the display looks and even affix it in the environment, in this case, overlaid on the table next to the book. Finally, as our last example, we've designed and evaluated methods to support location-based touch and gestural input on the user's own body, using sensor fusion with real-time computer vision and inertial motion sensors. In this video, a user interacts with VoiceOver on their phone simply by gesturing on their body.
Voice input. Daily summary. Health and activities, voice input, notifications. Notifications menu opened. You have 1 missed phone call and 2 new messages.
So on-body interaction leverages the user's proprioception and increased tactile acuity. We've attempted to develop intuitive mappings between the body and function. For example, here, the user will access the clock by touching their wrist.
Clock. Clock menu opened. Timer. Stopwatch. Alarm, set for 8 a.m.
This project was joint work with Professors Rama Chalapa and Leah Finlater, David Ross at the Atlanta VA Medical Center, and led by PhD students Lee Stearns, Jon E, and Jon E. It was funded by the Congressional Directed Medical Research Program. Just checking my chat to see if there's anything in there. Seems good. So our second project is in many ways great. Our second project is in many ways similar to our first, but in this case, the focus is on sound. That is, how can we leverage advances in sensing and machine learning to improve sound awareness for people who are deaf or hard of hearing? This work was inspired by Dhruv Jain, who in 2014 was a visiting student to our group from IIT Delhi, and now, I'm proud to say, is on the job market as a UW CSE PhD student. He is co-advised by me and Professor Leah Finlater. Let me begin by playing a video of Dhruv back in 2014, showing an initial head-mounted display prototype that we built, which visualizes where sound is occurring in a room. The video is shot as if you're wearing the HMD.
We are studying how heads-up display technology like Google Glass can be used to provide sound awareness for the deaf and hard of hearing via glance-labeled visualization. As someone with hearing loss, I rely on lip reading, non-verbal cues, and my hearing to decode speech. This works well for one-on-one conversation, but in multi-party conversation, my visual attention is split and I'm not able to ensure where I should look to lip read and observe body language.
The HMD prototype conveys sound direction and magnitude in real time. Here's another video showing multi-party conversation.
But I'll be right back in case you need me.
I just realized something. We've never had a completely successful test with any of the equipment.
I blame myself.
So do I.
So these are scripted conversations used in our user study. And I'm a huge Bill Murray fan. That is from Ghostbusters. So if you felt like that was familiar to you, maybe it is. So through user studies with deaf and hard of hearing participants, we solicited design feedback and preferences. While the early prototype was not fully wearable, the system enabled us to investigate feasibility. Our preliminary results show some potential as captured by this participant.
When we went back and forth, it was clear, it was like fun. And then to the ghost got you run when you were standing behind me and you froze. It was just like right there. So I knew you were speaking.
This work was conducted in 2014 and published at CHI 2015. And since then, I've had the pleasure of working on a variety of projects in related areas, including real-time captioning on HMDs, IoT smart home displays for people who are deaf and hard of hearing, and smartwatches for sound classification. This is a large ongoing effort with collaborators at Gallaudet University, UW, and the University of Maryland. Much of our work is driven by team members' own lived experience, as well as formative interviews and surveys. For example, in 2018, we conducted an online survey with 201 DHH participants with a range of communication preferences to understand their interest in and design preferences for and potential social implications of AI-based mobile and wearable sound awareness tools. To help ground feedback, in the survey, we showed a variety of scenarios, including smartphone, smartwatch, and head-mounted display sound feedback. We also showed different kinds of visual illustrations, like this one of a person using these devices on a busy street with a bird chirping, people talking, and a car honking. Overall, we found that there was high interest in sound awareness. 73% of respondents said very or extremely interested in sound awareness, and as of greatest interest were sounds like alerts, voices directed at you, sound identity, and sound location or direction. Our regression analysis also showed that communication preference is the strongest demographic predictor for interest level. People who preferred oral communication were most interested in sound awareness tools, whereas those who preferred sign language and were thus more embedded in deaf culture were least likely to be interested in sound awareness tools, an important cultural consideration. In terms of design preferences, 92% of the 201 respondents wanted haptic and visual feedback, and oftentimes they wanted it through two different devices. For example, the smartwatch might provide haptic signals or alerts, and then the HMD or smartphone might provide some level of visual feedback. But there was lower social acceptability for the head-mounted displays than there were for other devices, particularly amongst strangers. I want to turn now towards a specific project and highlight some of our design processes. Many of us have smart home IoT systems, like Google Home or Amazon Alexa, which rely on speech and audio interaction that can also present accessibility barriers. Increasingly, these IoT systems are coming with displays. I'm showing a photo of the Amazon Echo Show with a touchscreen that's displayed with a display that's placed in someone's kitchen. So our question was, how can we design smart home displays to support deaf and hard of hearing user needs? And what sort of features and attributes would someone want? Well, these questions and our data from our formative survey led us on a multi-year set of projects, beginning with formative interviews and a Wizard of Oz evaluation, followed by the development of a working prototype and 2 in-home evaluations, and then the emergence of a parallel thread, looking at using smartwatches. Let's look at the Wizard of Oz study. So the question here is, how can smart home IoT displays support sound awareness? For this initial work, we interviewed deaf and hard of hearing participants about their preferences for in-home IoT displays, and specifically for how the technology could support sound awareness in the home. We also solicited the reactions to design probes and visualization ideas. We explored 3 initial prototypes, shown here. A floor plan view that situated sounds within a blueprint of the house, a list view that showed a historic overview of sounds, and a waveform view that showed sound magnitude over time. For our Wizard of Oz setup, we had an actor conduct a series of tasks in a few rooms, such as making coffee, knocking on the door, running water, moving about rooms. The wizard, who was hidden, ensured that the participant's smart home display accurately visualized information about the actor's movement and sound. For example, here, the actor in the background is pouring coffee in the kitchen, and the display is accurately showing this information. For our study findings, we found that the most preferred display was in fact the floor plan, because it intuitively visualized the position of sounds. The location of sound itself holds a lot of informational power. Participants also suggested adding in additional information to the floor plan, like waveforms, history, and asked about the feasibility of automatic sound classification. Participants also expressed concerns about trust and confidence in the data, privacy, information overload, and the potential complexity of doing system installation. From this formative research, we began working on a real functioning prototype, which we call Home Sound. We began by modifying tablet computers with laser-cut frames. We then wrote privacy-centric sound processing code and created a series of real-time sound visualizations. Let's look at the primary screen, which shows an updated floor plan view from the Wizard of Oz study. For each room, we provided a dynamic circle that pulsated with sound magnitude and a waveform view of recent sound history in that room. We also, at the bottom, provided a location-based timeline of sound magnitudes over the past few hours. In this video demonstration, we'll show what happens when someone turns on the kitchen faucet and runs water. For our field studies, we deployed 3 to 5 displays in each home, much as you would having an Amazon Alexa in multiple rooms in your home. And this was dependent on the user's preferences. And we deployed these for around 3 weeks. Notably, each display contained its own microphone, and we sent privacy-preserving data packets to the cloud for networking across displays. So each display in a home showed the same sound data. Here's a longer form video demonstration by Dhruv Jain talking about this work.
Rather than inspired by my own personal experience as someone who had a parent, my project called the Home Sound contains a series of IoT displays deployed in different locations in the home. This is the server running on my desktop in my office, and it's connected to my home where the IoT displays and the smartwatch are installed. So let's say we have one tablet in a living room, one in a bedroom, and one in a kitchen. And these tablets sense the information in the environment and provide that feedback.
In our field deployment studies, all participants reported value in the home sound displays, and then it generally increased their sound awareness. For example, this participant 1 said, "I realized that my wood floors make a lot of noise when I walk." As a second quote, "I was working on my laptop. The system showed something making noise in another room. It was my dog barking." But we also heard comments like this: "I felt like it was fun to look at initially, but then I'm so used to living without sounds that I used it less in the end." So in summary, participants perceived utility, but this utility waned for some. Home sound increased awareness of activities in the home, from the mundane, like walking on a wooden floor, to dog barks and microwave beeps. And unlike in the Wizard of Oz study, no one expressed privacy concerns, but we had carefully explained how logged sounds could not be reconstructed. The 2 most common requested features were automatic sound notification and alerts. For example, I want to be able to use this system when I'm commuting to work, taking my kids to school, when I'm hiking or going to the beach or to a movie theater. And recall that in our formative survey, a smartwatch was also the #1 preferred feedback device for non-speech sounds. So this led us down an additional research trajectory, examining smartwatch-based sound feedback. Unfortunately, due to time, I'm not going to go into the details, but I suggest reading our recent Assets 2020 paper or downloading our SoundWatch prototype on the Google Play Store. This remains active research in our group, and it's currently classifying up to 20 sound classes with 81.2% using a lightweight deep learning model. This is the result of collaborations with many students and other faculty, which I do not have time to properly acknowledge, but I am deeply thankful for my collaborations and to the various funders. Finally, I want to turn to our last project on urban accessibility, which is also our largest. So here we're asking, how can we develop scalable solutions that map, assess, and visualize the accessibility of urban infrastructure? In particular, we've been focusing on sidewalks. So sidewalks are a critical public infrastructure. They fundamentally shape how and where we travel. For people with disabilities, sidewalks play a crucial role in supporting independence, quality of life, and overall physical activity. The problem is city streets, sidewalks, and businesses are not accessible. This is a famous picture of a wheelchair user stuck at a curb without a curb ramp from the disability rights movement in the 1970s. There's a lack of curb ramps still. This is from New York, a recent picture. Physical obstacles like this pole in the middle of a curb ramp. incomplete sidewalks, or surface problems due to weathering or natural growth. In the worst circumstance, you might encounter a scene like this with multiple problems that impede access and lead to unsafe conditions. This has significant negative consequences, as captured by one of our interviewees.
When I go to school in the mornings, I don't take the sidewalks, I actually take the street, and they shout at me from their cars. They're like, get off the road, and it's like, I can't actually use the sidewalk.
The problem is not just a lack of accessible sidewalks and pathways, but a lack of data. In fact, the US National Council on Disability notes there is no comprehensive information on the degree to which sidewalks are accessible in the US. And of course, this problem is not just unique to the US, but is endemic across the world, and I'll have some examples in my talk. So my group is pursuing a twofold complementary solution. First, to develop scalable data collection methods that mine massive repositories of online imagery to identify street-level accessibility problems using a combination of machine learning and crowdsourcing. And then second, thinking about ways in which we might be able to leverage this data to enable new urban accessibility visualizations and analytic tools to support disability advocacy, to support government workers in urban planning. For example, in the background, I'm showing a video of a beta version of our tool called Access Score. Here, users can get an at-a-glance custom view of the accessibility of their city based on the data we're collecting. Our overarching vision is to develop crowd plus AI techniques to map and assess every sidewalk in the world. And we've been working on this problem for a long time, and we will be working on it for a long time in the future. From running formative interview studies with stakeholder groups, such as people with mobility disabilities and transit departments, to building and evaluating data collection and visual analytic tools. So let's take a look at some of our initial remote data collection tools. The question we asked here is, can minimally trained crowd workers find and label sidewalk accessibility problems in streetscape imagery? To address this question, we iteratively designed and developed an initial crowdsourcing system comprised of a labeling interface and a verification interface. Here's a demo of the labeling interface.
Your job is to find and label all sidewalk-related problems. In this case, there is a fire hydrant in the sidewalk, so you draw an outline around it. Outlines are drawn by clicking around the identified problem to set outline points, with a final click at the original point to complete the shape. When the shape is complete, you select the appropriate label. In this case, we select Object and Path, and then mark its severity. Severity is a 5-point scale where the far right is most severe, indicating not passable, and the far left is least severe, indicating passable for wheelchair users. Here, we mark 5 because it is clear that a wheelchair user could not get past this fire hydrant. Let's look at a few more examples. In this example, the sidewalk is badly cracked. So again, we draw an outline by clicking points around the offending area. In this case, rather than selecting Object and Path for our label like last time, we select Surface Problem. It's also a less severe problem than before, so we select a 3, which indicates that the area is hard to pass for wheelchair users. For our third example, the sidewalk ends abruptly in the grass. This may force wheelchair users to travel on the road. So we draw an outline around the end of the sidewalk and select Prematurely Ending Sidewalk. As you label these images, please know that there could be more than one problem in an image as shown here. You should try to label all problems in each image.
We also tested our early interfaces and solicited feedback from wheelchair users. In this video, a person in an electric chair uses an initial prototype to rate accessibility problems.
Okay, definitely this utility pulls an object and path. Okay, object and path. I'd say that's a 5.
In addition to labeling, we designed and evaluated the crowdsourcing verification interface. Here, it's a 3-step process. You can verify the label, verify ratings, and provide details. So for example, in this intersection, it's missing a curb ramp. So this is marked correctly, and in verification, you would select yes, or that check mark to select agree. But sometimes users also make mistakes. Notice that this fire hydrant is also outlined. This is not a barrier. There's actually plenty of room for a wheelchair user to go around the fire hydrant. So this is a mistake, and you would click no. For our crowd worker experiments, we deployed our tools to Amazon Mechanical Turk, an online crowdsourcing marketplace. In all, we hired 185 labelers and 273 verifiers who completed 7,500 labeling tasks and over 19,000 verifications. The important point is, we found that verification is much faster. While it took 35.2 seconds to label an image, it was over 3x faster to verify an image. So are minimally trained crowd workers capable of finding accessibility problems in online map imagery? With a single labeler per image, accuracy ranged from 85% for the sidewalk ending category down to 73% for the object and path category. And I'm showing actual labels from our study. There are 3 common labeling mistakes. Most frequently, over-labeling. Truckers had a tendency to mark superfluous objects as problematic. For example, I'm showing a stop sign that's not actually in the sidewalk. It's next to the sidewalk and is not an obstacle. And then less commonly, we saw some vandalism or random labels, as well as categorical errors like putting surface problem when it was really an obstacle in path. To investigate the effect of quality control techniques, we ran experiments with multiple labelers per image and calculated majority vote accuracy across 4 group sizes: 3, 5, 7, and 9. While a single labeler results in 81% average accuracy for this task, this increases to 90% using majority vote with 9 labelers. You'll notice that it saturates roughly around 5 labelers, but having 5 labelers per image is still very laborious. So we evaluated the effect of verifications, which, as you might recall, are 3 times as fast as labeling. The axis on the bottom increases in time, cost, and labor from left to right. We get a significant accuracy boost using 3 verifiers and only 1 labeler, so it's 88%. If we hire 3 labelers and 3 verifiers, this is more efficient than hiring 5 labelers, and we get 93% accuracy. So in sum, crowd workers can find accessibility problems in static imagery with an accuracy of 93%. But can we do better? This relied purely on manual labor. What about machine learning or computer vision? So that's what we began exploring next. Our first system in this space was called Tome, which semi-automatically detects curb ramps in Google Street View imagery by combining crowdsourcing, computer vision, and machine learning. Tome is comprised of 6 components: a custom web scraper that downloads street intersection data from Google. For each intersection, we download the Google Street View panorama, a 3D point cloud, some top-down Google imagery, as well as some GIS metadata. And then for our study data set, we looked at 4 cities and a total of 11.3 square kilometers, which included over 1,000 intersections. Tome's third component is a computer vision-based curb ramp detector that takes in a Google Street View panorama and attempts to detect curb ramps automatically. But as you might imagine, automatically detecting curb ramps is a difficult problem. While we're able to detect some curb ramps automatically, that's a true positive, there are also false positives. So like the algorithm in this case is marking part of a road as a curb ramp, and it's not actually a curb ramp. And then most importantly for our work, the algorithm results in false negatives, not actually finding a curb ramp when one exists. And this is the most expensive error to correct. So to address this problem, we created a smart task allocator that uses machine learning to try to predict the difficulty of a scene for computer vision and either routes the labeled scene to a manual verification interface, which is fast and cheap, or down to the crowd, which is more accurate but slower and more expensive. Let's dive a bit more deeply into how the automatic curb ramp detector works. We use a 3-stage algorithm. In step 1, a deformable part model, which at the time was state-of-the-art in computer vision, and we slide it using a sliding window algorithm across the entire panoramic image. It detects areas that look like curb ramps. Detections here are shown in red boxes. Brighter red corresponds to higher confidence. In the bottom left of your screen, I'll track the number of detections and errors throughout the 3-stage algorithm in this table. So you might notice first that there's multiple overlapping redundant boxes. You might also see that there are curb ramps detected on skies and in roofs. These are not errors that humans would likely make. So our second stage post-processes these detections. Recall that we have a 3D point cloud from the Google Street View car. we're able to automatically eliminate things above the horizon. But the 3D data is too coarse to help actually identify curb ramps. We also apply non-maximum suppression to remove overlapping labels, which brings us down to 5 false positives. Finally, in the final stage, we take advantage of the fact that street intersections have highly constrained geometries, and we train an SVM to incorporate additional contextual information. This helps eliminate additional false positives, including driveways or other things that kind of look like curb ramps but are not at a corner. So now we're down to 3 false positives, which can quickly be manually verified. For scenes that are predicted to have no false negatives, we send them to this crowd verifier, and the interface looks like this. Here you're seeing a user quickly pan through an intersection and eliminate spurious detections by the computer vision algorithm. Again, this is very fast for a human to do. For scenes that are predicted to have 1 or more false negatives, the task allocator routes the work to the labeling interface. In this video, again, the user is going to pan around the intersection, but this time they're actually doing labeling work, which is more laborious. They're drawing polygonal outlines along the curb ramps in this video. And again, we used Amazon Mechanical Turk to run a series of experiments. We hired lots of people. They did many tasks. The important thing is, again, verification is a much faster thing for humans to do than the actual labeling task itself. And so we can leverage this in our systems. To evaluate Tome's performance, we first examine 2 baseline conditions. The first is manual labeling alone. The second is just computer vision with some manual verification. And finally, it's the Tome system itself. I'll show precision in blue, recall in orange, and the aggregate F measure in green. Higher is better in the graph. So with manual labeling alone, we achieved an F measure of 86%. With computer vision plus verification, the performance drops, as we might expect, to an F measure of 63%. But with Tome, we achieved similar results to the pure manual pipeline, but the per scene processing time is reduced by about 15%. So this research demonstrates both the potential and complexity of building Human+AI workflows. Building on Tome and others in the interim culminated in the design and development of Project Sidewalk. Project Sidewalk is a web-based crowdsourcing tool for collecting sidewalk accessibility data at scale. The tool is open source and publicly deployed. Right now, you could visit at projectsidewalk.org. Project Sidewalk combines online map imagery, remote crowdsourcing interfaces for labeling and validation, and machine learning to scalably map and assess sidewalks. Working with our partners, Project Sidewalk is being used to improve urban planning, build new interactive visual analytics for urban accessibility, and improve government accountability. Let's take a look at a demo. With Project Sidewalk, users are given game-like missions to label and assess sidewalk accessibility by virtually walking through city streets using immersive streetscape imagery. This is a little bit like a first-person video game, and we take advantage of that with game design principles. Here, you scan and look for problems, and you can label them by selecting the appropriate button. You can mark a severity, enter open-ended comments. Here you're seeing someone label a curb ramp, and at that same intersection, despite there being a crosswalk, there is no curb ramp, so they label that as well. And here we're seeing a fire hydrant and a pole in the middle of a sidewalk, as well as missing sidewalks. Crucially, anyone can contribute. You just need a computer and internet connection. Here, a child in Germany is labeling a neighborhood in Mexico City. Project Sidewalk has 2 game missions, exploring and labeling, and validating and correcting. As you saw in the video, each time a user labels a sidewalk feature or barrier, they supply a severity rating, open-ended descriptions, and optionally add tags. And we have lots of different tags, and we work with our partners to figure out what tags are most important to them, 37 in total currently. So for example, with the obstacle tags, these include things like trees, fire hydrants, vegetation, parked cars, poles, garbage recycling cans. All of these things impede access. In addition to labeling, we also have validation missions to improve and ensure data quality. So I don't know how this is going to work with the web seminar, but we're going to try something, which is you are going to be like a Project Sidewalk user right now. And I am going to give you a series of validation tasks, and you're going to tell me whether or not you think they're correct. So I was expecting to use chat, but since we're in webinar mode, I don't know how you can give me that feedback. So this is going to be an experiment for us all, and maybe a chance for us to wake up. Here we go. So maybe somebody needs to take a risk who's just an ordinary attendee and try to figure out how you can communicate with me. Not seeing anything.
If we have volunteers, they can add their name in the chat and we can give them permission to speak. So we'll see Michael, I think.
Okay, perfect. Michael could, yeah, so I don't know if Michael is a co-host or not, but yeah, okay, so Michael is modeling the behavior that I was sort of expecting and wanting, which is, I'm now gonna show you a series of these, and you could just say agree or disagree or unsure in chat, and don't hesitate. So Michael, I agree with you. This is actually a missing curb ramp. It's a pretty significant barrier here. There's a crosswalk, though faded, but there's no curb ramps. Here's another example. This one's from Washington, D.C. Do we agree or disagree? Maybe it'll just be Michael and I playing this game. Is this an obstacle and path? Michael disagrees. So we've got the poles marked. Oh, wait. Oh, Matt also disagrees. Well, I would agree. These two poles cannot be passed. Oh yeah, look at the blue dot, or it'll be different colors depending on what the problem or accessibility feature is. Yeah, okay, good. Well, we're training up here, Michael. Okay, thank you, Matt, for participating. Here's another one. In urban planning, we call this an uplift. The tree roots have uplifted the sidewalk panel. Is this a surface problem? Yeah, now we're having some fun. Awesome. Yeah, great. Okay. Yeah, I agree. Great. Okay, how about this one? Here we're seeing a picture of, sorry for not describing these. We're seeing a picture of a label on the grass next to the sidewalk. Disagree. Yes, that's correct. See, it's not on the pedestrian pathway. How about this one? This is a pole or a street pole. It's at a controlled intersection. And someone marked the pole as an access obstacle. And I also disagree with this one. There's plenty of room for a wheelchair user or other people who use mobility aids to go around that pole, so not a problem. How about this one? This last one shows a grassy area with no sidewalk at an intersection. It's an uncontrolled intersection, and it has a missing curb ramp label. So is this a missing curb ramp? Yes. Well, when we talk to our partners, this is what is the most challenging. Technically, no, because there is no sidewalk here, but you might want to mark it just to indicate your desire for one. That is, you could also mark this as a missing sidewalk, but some people mark this as a missing curb ramp. So we also try to make thank you for participating in that activity. I hope that got the blood flowing. Okay, so we also try to make Project Sidewalk fun and educational. To help encourage and sustain participation and divide work, we assign users missions and use game design strategies to reward achievements. We have things like leaderboards. We also have interactive tutorials like you would get in a game. In 2017, we launched an initial pilot in Washington, D.C., and over 1,400 users participated, providing 260,000 sidewalk accessibility labels with 92% accuracy. I'm showing the data that we collected behind me in a top-down map where each of the geolocated points is colored by its access feature or problem. So for example, missing sidewalks are purple and curb ramps are green. To explore patterns in sidewalk accessibility, we can visualize this data in a variety of ways. For example, this map shows DC streets colored by street accessibility based on a scoring algorithm that we created. There's lots of different ways that we can visualize this, and my PhD student, Manaswi Saha, is doing this in her dissertation. This one is a point visualization. Through this, we might be able to identify some hotspots, such as these two highlighted areas for where there are a high density of obstacles in Washington, D.C. Here, this is a aggregate density heat map, which helps make those problem areas even more salient. Here, bright colors correspond to more problems. One bright spot corresponds to Anacostia, which is a lower socioeconomic area that is 92% Black, and our findings suggest has poor pedestrian accessibility. But another bright spot corresponds to Georgetown, a highly affluent area that is 82% white, but has historic preservation policies that perhaps negatively impact accessibility. This is the potential of data-driven urban analytics for accessibility and what my lab is really excited about for the future. Since our pilot deployment in DC, we have worked with partners and NGOs to deploy Project Sidewalk into 7 additional locations, including 2 in Mexico. Over 10,000 users have contributed nearly 650,000 labels and 175,000 label validations. We believe this is the largest open image-based sidewalk accessibility dataset in existence. And all of our data and tools are open source, so others can build on our work or maybe laugh at our source code. For example, a developer named Barbara Moreno built this interactive tool visualizing sidewalk accessibility data in DC from Project Sidewalk data, which nicely received some local press. But we've seen other people integrate this into their tools. This one is the Geo Open Accessibility tool. This one comes from a user who just imported it into cardo.com because we use GeoJSON, which is a standard format. And I want to return to some of our deployment sites to highlight how Project Sidewalk has been used by community advocates and municipalities. Starting with Newberg, Oregon. This is a city about an hour outside of Portland with a population of about 24,000 people. Behind me, I'm showing a screenshot of their public works page, which lists Project Sidewalk. Over 230 users participated, completely mapping and assessing 187 kilometers of streets. And again, visualizations can help us discover patterns in the data. For example, a lack of sidewalks around the city's periphery. But most excitingly to us, as a result of our deployment, the Newberg City Council passed new sidewalk accessibility policies, including $50,000 for immediate sidewalk repairs on city property. Let's turn now towards our first international deployments, which are in Mexico. We're particularly excited about opportunities to work with under-resourced cities on Project Sidewalk type deployments. In Mexico, we worked with a local NGO to deploy Project Sidewalk in San Pedro Garza Garcia and Mexico City. Each city represents a different type of partnership. In San Pedro, we partner with the local government and schools, while in Mexico City, it's more grassroots. In our work with the San Pedro government, they state, Project Sidewalk provides us with data that is essential to improving San Pedro's urban accessibility. With Project Sidewalk, we know the main problems to be solved, how many problems there are, and their location. The results will be used to inform a new pedestrian master plan for our municipality. Our Mexican deployments are in close collaboration with Liga Peatonal, a Mexico-based NGO focused on pedestrian improvements in Latin America. And they helped us translate everything on our website into Spanish, which I'm showing as a screenshot, and also adapt our interface to have Mexico-specific labeling tags and culturally relevant details. Here's a video demonstration of the Spanish language website labeling streets in Mexico. So they're selecting missing curb ramps for that intersection. They're also going to mark the lack of a crosswalk. You have a faded crosswalk painting here. And then they're going to move around a bit, mark the curb ramp, but notice there's also rocks there. So they're going to mark that as a accessibility barrier and then continue to do their explorations. So thus far in Mexico City, over 500 users have contributed 32,000 labels, but there's still much work to do. In our pilot neighborhood, we're at 41% completion. In San Pedro, we've completely audited 1,300 kilometers of city streets, providing over 100,000 labels and 37 validations. And one of the things that's happening with Project Sidewalk right now is we're expanding the ecosystem of tools and really building out a lot of visual analytics. So this is an example of the label map tool, which allows you, for example, to filter down and look at just specific label types. So here I'm showing you obstacle labels. Here we're visualizing just missing curb ramp labels. And here we're looking at missing sidewalk labels. And you can like zoom in and you can start to begin to see patterns. So for example, the mountainous and more peripheral edges of the city systematically lack sidewalks. And recall that we asked users to rate the severity of identified issues on a scale from 1 to 5. So there's another thing that you can do is you can zoom in into the most severely rated areas of the city. Here are all curb ramps found in the city rendered as bright green dots. And here is a subset rated as the worst quality. Because Project Sidewalk is an image-based labeling tool, we can click on the dots and see the original label and image. And then using a tool we call Sidewalk Gallery, we can easily look at other poorly rated curb ramps and identify patterns. For example, the most problematic curb ramps in our 2 Mexico cities are too narrow, steep, contain obstacles, or fundamental design flaws. The tool sidewalkgallery.io allows you to do these kinds of explorations. It's a filterable gallery of all 600,000 crowdsourced sidewalk accessibility images. And we think this interplay between quantitative and qualitative analysis is really powerful. And it demonstrates some of the future work for Project Sidewalk. So I'm running low on time. I'm going to skip forward just slightly here. But the next part of my talk was really outlining some of the things that we're most excited about doing in Project Sidewalk. The first is working with urban planners and geographers to begin to really deeply dive into our data. So like, what are the geospatial patterns and key correlates of sidewalk accessibility? How does accessible infrastructure correspond to racial and socioeconomic factors? And we've done some initial analysis in this area that I'm just going to breeze over here due to time. As a second area, we have this growing massive data now, this labeling data set. So how can we leverage our growing data sets to improve our machine learning models? We have some initial work here at Assets 2019, training a deep learning model, a residual neural network on 2 different kinds of labeling tasks. And how might we integrate this backend into Project Sidewalk and create new hybrid AI and human workflows? And again, I'm just going to skip over these results so we can get towards the end and have time for questions. And then finally, is the third area of future work, we're really interested in spatiotemporal change. So like what are the spatiotemporal patterns of how urban accessibility is changing? Where is it not? What are the correlates to this along racial or socioeconomic status? And one of the things that we're using is going back in time with Street View. Google Street View now has the ability to look at historic imagery. So I'm showing a movie behind me of using Google Street View to look at how sidewalk infrastructure might change over time. In this case, it's actually improving. In this case, it will also improve. This is in Washington, D.C. You'll see that they're adding sidewalks, which is pretty cool. So I want to study these types of changes. Here, this is New York City, a recent photo. Here it is back in 2007. So they've had missing curb ramps in New York City for a very long time, and so on and so forth. These are the kinds of analyses that I want to do. And I want to give you an example of some of the prototypes that we're building with crowd plus AI techniques. And then we'll close for questions. So we've created 3 early stage prototypes, which differ in labeling technique, but they combine some of our deep learning models along with human labeling user interfaces. So for example, with prototype 2, we have a large labeling area for the selected time shot and a grid view of 12 time series images dating back 10 years for that same intersection. And the red dots, which are really small on your screen, show where the computer vision believes there are curb ramps. So let's take a look. Right now, we're going to outline a curb ramp, and notice how that boundary box is immediately propagated to all time series. So I drew only one bounding box, and then it was automatically back propagated into previous time series imagery. Now I'll outline the other curb ramp. And again, with just those 2 operations, now I'm going to go quickly and clean it up a little bit because some of the propagations are wrong, but I was able to label 9 time series imagery very, very quickly. So this is kind of the power of combining some of the human plus AI models. And I'm not going to have time to go into our other prototype, which allows you to see the full panorama as you're labeling it, but is pretty similar to the second prototype. So in conclusion, I invite you to join our efforts in using Project Sidewalk to map and assess sidewalk accessibility. You can follow us on Twitter or visit projectsidewalk.org. And this has been a massive undertaking. I just want to point out the amazing set of collaborators and students. In particularly, Manaswi Saha is graduating this year, and Mikey Sogstead, who's right next to them in this photo, is our full-time research scientist and lead engineer. And we could not do this work with Project Sidewalk without our partners. They have been absolutely essential, as have our funding sources, and we've been thankful and grateful to have a variety of different kinds of funding sources. If you're interested in finding out more about any of this work, you can go to makeabilitylab.io, which is our lab website.